Thanks, Vince. This is a joint work with Noga Alon, Michal Feldman, Ishai Mansour, and Moshe Tenenholz. And I want to tell you about today about the dynamics of evolving social groups. Let me start by telling you what I mean by evolving social groups. So these are groups in which the current group members are the ones who are selecting which new members will join the group. So one example which will be clear to anyone in this room is academic departments. So in academic departments, the current faculty members are the ones who are selecting which candidates will join the department. Another example from the academic domain is the National Academy of Sciences, where current members suggest and vote on which new members will be admitted. An example from a different domain is from the Freemasons. So if one wants to join a Freemasons lodge, almost all of the current members of this lodge need to approve of his admission. Different examples are condos. So if one wants to become an apartment owner in a condo, he first needs to pass an admission committee, which is composed of the condo tenants. Now, the very high-level question that we want to ask here is what are the effects of different admission rules on the group composition as the group evolves? And I'm going to be a bit more formal about this question in the next slides, but I first just want to tell you that this question can be asked in two settings. So first, we have a setting in which the group grows, so it doesn't have a constant size, like an academic department or the National Academy of Science. And we can also consider the same question in a setting where the group is of a fixed size, like a condo tenants, so the number of apartments is fixed. And we have results for both settings, but for most of this talk, I'm going to concentrate on the setting of growing groups, and I'll just mention some results for fixed groups at the end, if we have enough time. So let me define our model for growing groups. First of all, we assume that all of our group members have opinions which are real numbers between 0 and 1. This kind of modeling is pretty standard in political science, for example, where there are the opinions model where 1 is on the political spectrum between left and right. If we are considering an academic domain, then these numbers can be how theoretical or applied one's research is. In any case, we assume that our members have these opinions, which are between 0 and 1. And throughout the pictures that I'll have in this talk, it will be useful to put each member on the location corresponding his opinion. And you will see why soon. Now we're going to analyze a process that works in discrete time steps. At every time step, we assume that two candidates will arrive. They want to join the group, and each one of them has an opinion drawn from the uniform distribution. And now our current members need to decide which member to vote for. And we will assume that we'll use a very simple voting rule. So each member is going to vote for the candidate who is more similar to him, who is closer to him on the real line, simply because he wants to make sure that the group will be more similar to him. He will have a nicer experience in this group. And let me take just a very short detour on explaining a bit more about the rationale behind this voting rule. So one of the well-studied forces in sociology is homophily. This is the tendency of people to prefer and interact more with others who are more similar to them. And this tendency can manifest itself in various dimensions. So fixed ones like age, gender, race, to more behavioral ones like hobbies and opinions. Just to give you a rough idea on how it looks like, so this network is the friendship network in some high school, and different colors correspond to different races, and it's easy to see that this network is pretty homophilous with respect to the yellow and green color. So this is homophily, and this is the reason why we assume that our members are voting for candidates that are closer to them. So they are behaving myopically. Yes?
Just answered it.
So they are behaving myopically, and what they're trying to do is for the short term, making sure that other members that are closer to them will be admitted. Yes?
How did you decide on two candidates in each time step as opposed to another number?
I guess it's natural. It is natural to start from two candidates, and already very interesting things happen for two candidates.
It's not interesting because everyone will just converge. If you just pick one person in each.
You mean two candidates as opposed to one candidate?
Yeah, or I mean any other number, but
I mean, one candidate, you can think of a variation of the model, but if you want the simplest model in which there is actually a bit of a richer choice, so a choice between two, the two seems like the minimal number, and it's still good enough to get interesting things going on. I'll talk at the end a bit about extensions, but yes, definitely extending this to more candidates is interesting. And we have some ideas on how to do that. Okay. So each one of the members votes myopically for the candidate closest to him. And our admission rule basically takes all the votes of the members and applies some function to decide which candidate is accepted to the group, if any at all. And let's explore a couple of admission rules. Let's start with a very simple one. So consensus. This means that a candidate will be accepted to the group only if all the group members agree that this candidate is better than the other. And initially, one can suspect that some strong requirement like this should make the group be quite homogeneous, since we need the consent of everybody in order to admit someone to the group. But it's actually not hard to see that the exact opposite thing is going to happen. So let's see why. There's an easy way of thinking about how the members will vote. So we can draw this line, and this red line is simply the average between the opinions of the two candidates. Now, since every member is voting for the candidate who is closer to him, this means that all the members on the right side will vote for the right candidate. All the members on the left side will vote for the left candidate. Now, since we require all the members to vote for the same candidate, since we require consensus, this means that we'll accept the candidate only in the case that this red line is to the left of the green guy. And since this red line is the average between the opinions of the two candidates, this means that both of the opinions are in this leftmost interval, or this red line is just to the rightmost of the right candidate. So in this case, the opinions are in this red interval. So in general, only candidates in these two red intervals can join the group. Now, since there's always a positive probability of accepting a candidate here and here, since it's possible that both of the candidates will be just right of the rightmost candidate and left of the leftmost candidate, this means that as time goes by, these red intervals are just going to shrink and go further and further towards 0 and 1. Yeah.
I'm sorry, I don't see how you get two candidates in your picture when you draw the one line.
So the one line is just the average between the opinions of the two candidates. So I'll have a slightly different picture in the next slide, and I think it will be clearer then. Let's wait with this for like 2 minutes, okay? And if it's still, this is the reasoning about this average and how the members' votes is going to repeat several times throughout the talk, and I think it will be clear in the next slide. So, this one, okay? Okay, let's ask me again if it's unclear. Okay, so the corollary here is that the consensus admission rules, which initially seems like it's something that should result in a homogeneous group, actually it's doing the exact same opposite. We get a completely polarized group. So let's consider another simple admission rule. So,
just so I understand that.
Yes.
If someone is to the left of everyone and the other guy is somewhere in the middle,
yeah,
then nobody wins unanimously.
Exactly.
One guy's to the left of everyone, and the other guy's to the. And where's the other guy?
So both of them have to be either in this interval or either in that interval. So the average between them has to be either here or here. Okay? So. Yeah.
So at some point here, you'll just stop it.
Yes, that's correct.
So does that count as polarization? It's more like a freeze at some point.
You're right that you can also think about it. It's polarizing, yes, and more than that, as time goes by, it will take you more and more and more time till you admit another candidate. So yes, you're definitely right.
So
yes, Ida.
One interesting thing about this rule is it violates independence of irrelevant alternatives, which means if a second candidate shows up, we are not choosing him, but he will undermine me from being chosen now is that in the examples that you gave, how does that, I mean, maybe it happens in our faculty meetings sometimes, but how often does that happen?
So I'm not sure how often people really use complete consensus also, how often people really use this rule, but you are right, that's a good point. I'm not sure exactly how often it happens.
Would almost complete consensus have the same effect?
What?
Almost complete. So you don't have but I don't think
So I'll talk about this. Yeah, this is one thing we're going to talk about in the next slides. Any other questions? Yes, you and I.
The group always grows, no one leaves the group ever?
Yes, this was at the beginning I said there are two settings. One is the setting of a growing group, and the one is a fixed group, so this is the growing group setting. Okay, let's move for the majority admission rule. So now we assume that the candidate that is voted by at least half of the group is admitted, and for the majority admission rule, it's actually the case that at every time step a candidate will join the group. And we can write this sum admission rule in a slightly different form that will be easier to work with. So the candidate that is closer to the median of the group is admitted. So again, we have all the members of the group on this line. Okay? And now we have the two candidates. Jason, to your questions. And this line is the average between the opinions. So all the people in this side are closer to the right candidate more than to the left candidate. So they are going to vote for the right candidate. And all the people on this side are closer to the left candidate. So they're going to vote for the left candidate. Now, since we require the candidate that joins the group to have at least a majority, then this means that the candidate that will join the group is the one that the median is on his side, on the side of the average closer to him. So basically, the candidate closer to the median is the one that is admitted to the group. So that's the nice description of the rule to work with. And what we show is that basically, regardless of the initial conditions, the group is going to become a center group with a triangle-shaped distribution, and its median is going to approach half. So just to give you a sense on how this looks like, these are pictures from a simulation we ran. So we started this group with, I think, two members, one located at 0.2, the other one is located at 0.8. And this picture here, every point is the member that was accepted every round. The height is his opinion. You can see a lot from this picture, but you can see that the middle area here is much denser than the areas on the side. And to give you a better idea of how it looks like, this is a histogram of the opinions of all the members when the group reached a size of 20,000. Okay, so it looks kind of like this triangle. And I want to give you some intuition on how we prove this theorem. And the main part of proving the theorem is showing that the median converges to half. So I'll do it in the next slide. And now I just want to give you, to explain why once we have that the median converges to half, the distribution will converge to this triangle distribution. Or more specifically, it will converge to this distribution. So let's assume for a second that the median is located at exactly half. So this means that if a candidate is located at x is less than half, then he has a probability of exactly 2x to be admitted, since this is the probability that the candidate that is more far from him will appear. And since we have two candidates, to compute the density function, we should multiply this by 2. Now, once we have that the median is not exactly at half, but close to half, this becomes a bit more noisy, but it's still the case that the distribution will approach this triangle distribution. So let me give you some intuition on why the median converges to half. And we'll need a bit of notation. So first of all, we denote a group of size k by sk, and its median by msk. And formally, we show that for any group of size sk0 and any epsilon greater than 0 with high probability, there exists k epsilon such that for every k prime greater than k epsilon, the distance between the median of the group and half is less than epsilon.
Quick question?
Yes.
Once you know the median converges, the half follows by symmetry, right? So it's really the fact that it converges to anything that's the...
think you're right. I think that's correct. The proof actually prove both together. So
it sounds like one is easier.
Don't think so. No.
But that's assuming it converges to a constant. You don't know that it converges.
Yes, converges to a constant. Yes.
They depend on the history and sometimes.
The whole point here is that it's independent of the initial configuration.
I see. Okay.
Yeah.
And the half is independent of the initial configuration.
Okay. So what is the proof idea? So we're going to consider a group of size k, and we assume here that k is large enough. And furthermore, we assume that initially we started the group from size 1, and the group grew using our majority admission rule till it reaches size of k. And at this point, the median is located at half minus epsilon. Epsilon here is greater than 0. So this is our group, somehow here, and this is the median. And we first show that when we double the group size, the median moves right by about 2 epsilon squared k members. So this is our old median, this is the new median, and about 12 epsilon squared k points between them. Now it's possible that these 2 epsilon squared k points are really concentrated in a very small interval of negligible length. So in the second step, we show that every 2 epsilon squared k consecutive members actually lie in an interval of length at least epsilon squared over 2. And these two steps together, roughly speaking, imply that after about 1 over epsilon squared double length, the median gets to a distance of epsilon over 2 from half. So it's actually getting closer to half. And in the next 2 slides, I'll give you some more intuition on how we prove these steps, and then I'll tell you why this idea is not very accurate. Yes?
So what happens for a different distribution from the uniform?
So we only study the uniform distribution. That's also the interesting extensions.
I'm going to convert to other distributions.
We don't. I'm not sure what will happen for other distributions.
Like candidates are not independent or something.
It's the same. You just normalize by quantile. Because you only care about which side you're on. So.
Okay. Sure.
Yeah. And I.
Both of these steps are true with high probability, probably, or something like that, or.
I mean, it's everything with high probability, but that's not the problem.
No.
Okay. Yeah, everything is roughly speaking high probability. Yes, that's just an intuition. It's not a complete formal proof. Okay.
To work with the quantiles because this is real. If there is a real Euclidean distance, so you cannot translate this to quantiles because quantiles, equal quantiles, they don't have equal Euclidean distance.
What does Euclidean distance have to do with this?
Sorry?
What does Euclidean distance have to do with the median?
People's preferences and this can be
Whether you go x right or
On a different distribution, I'm saying. Translate the idea of translating to quantiles is not going to work unless you also do the same transformation of distance.
Okay. When doubling the group size, we want to show that the median moves right by about 2 epsilon squared k members. So let's say that the quantity the median is here at half minus epsilon. And I'll first observe that by symmetry, the probability of accepting a candidate here is the same as the probability of accepting a candidate here. And these 2 intervals have the same lengths. Both of them have candidates on the same distance from half minus epsilon. So we can assume that, very roughly speaking, in the k steps that we increase the group from size k to 2k, the number of candidates that will admitted here and here is the same. Now in this gray interval, the probability of accepting a candidate is 4 epsilon squared, since this is an interval of length 2 epsilon. And the only way of accepting a candidate in this interval is if both candidates lie in this interval. This happens with probability of 4 epsilon squared. So again, with high probability, roughly speaking, about 4 epsilon squared k candidates will join this interval. So this means that the number of candidates that joined to the right of this median is greater by 4 epsilon squared k than the number of members that join to the left of this median. So the median has to move right by 2 epsilon squared k points. Now we want to show that these 2 epsilon squared points lie in an interval of size which is at least epsilon squared over 2. So recall that we started our group from size 1. So we had 2K rounds in which we admitted a candidate. Yes. Oh, good. We had 2K rounds in which we admitted candidates. So overall, we observed 4K candidates. Since our candidates are drawn from the uniform distribution, at every interval of size delta, we've seen about 4 delta K candidates. This is an upper bound on the number of members we accepted to this interval. So overall, our 2 epsilon squared K points have to lie in an interval of length at least epsilon squared over 2. And from these 2 steps together, we get that after about 1 over epsilon squared double length, the median gets to a distance of epsilon over 2 from half. Now, what's wrong with the proof, with this intuition? The problem is that we assumed here that the median, MSK, stays at the same place all the time for all the K rounds in which we increase the group. And it's not really correct because the median keeps moving. Each time that we admit more members, the median slightly moves. And this also affects the probability of accepting candidates to its left and to its right. So this is something that we need to really take into account and work much harder in order to take care of. So we've been talking about the consensus admission rule. We've seen it converge to some kind of a polarized committee, and also about the majority. We've seen that it converges to a triangle distribution. Now I want to talk a bit about what happens in the middle between the two. And we'll do it in a slightly different model. So this is a model where the group has a founder. The founder is located at 1, and he's the one setting the atmosphere for the group. So we give him a very special veto power. Only the candidate that this founder prefers might be admitted to the group. And since this founder is located at 1, this implies that only the right candidate can be admitted to the group. Now this right candidate will be admitted only if R greater than 0 fraction of the members in the group actually prefer the right member over the left member. So if, for example, R is greater than 0.4, then no one will be admitted. But in this example, if R is less than 0.6, then there's enough consent to admit this right guy to the group. And for these veto admission rules, and again, similar to what we did before, we can have an alternative description of this rule. So now the right candidate is accepted only if a fraction of at least R of the group lies here, or in other words, the y minus R quantile of the group is here, is above the average of the 2 candidates. Since this means that a fraction of y minus R of the group is to its left, and a fraction of R of the group is to his right, lies here. So for these veto rules, there's something quite interesting happening. We have a phase transition when R equals half. So if R is greater than half, then this process is going to behave quite similar to consensus. So as time goes by, we are only going to accept members closer and closer to 0. But when R is less than half, this is going to behave pretty similar to the majority admission rule.
0 to 1?
To 0. It's exactly the opposite. So the founder is at 1, and what happens is even if this founder has this power of only accepting the right candidate, still what's going to happen is that with time, only candidates closer and closer to 0 will join the group. So in some sense, it's much stronger result. So when R is less than half, then this is going to converge to a continuous distribution, a truncated triangle distribution, and this is quite similar to majority. So I was planning on giving you some intuition on how we prove this theorem, but I'm going to skip that. I just want to show you, this is the picture of how the truncated triangle distribution look like. So basically, this is a function of R. P here equals y minus R. And as R gets closer to 0, this gets closer to being a straight line. And where R is about a half, then this will be a triangle similar to the majority. let me, I guess, get to the summary. Sorry. Okay, so we talked about a model in which members of a group select new members based on their similarity, based on homophily. In our model, different admission rules have very different applications on the range of opinions in the group. If we require consensus, then the group is going to become polarized. Majority, the group will have this kind of triangle-shaped distribution. And in the middle, we have an interesting phase transition. So for the special veto rules, we have that it either will behave similar to a consensus or it behave more similar to a majority. Now, since we use the homophily as the driving force behind the members' votes, this work is related to works on opinion formation and cultural dynamics that, very roughly speaking, also consider questions such as how homophily affects the opinion mix in a network. And there are many natural extensions, as people here already suggested. So considering K candidates that arrive at any round, or candidates that are drawn from a distribution other than the uniform. Also other admission rules. So for example, just the P majority, so 0.75 prefer one candidate over the other without the restriction to veto rules. But I'm going to stop here, so thanks. Yeah, David.
What happens if your group members are not myopic? So
That's an excellent question.
I'm worried that if I take someone who's a little to my right, that will mean our party will slide to the right, but there isn't far left that we can slide, so I'm pretty safe taking someone much further.
You're right. That's an excellent question. We don't know. Yeah. Yes, Eva?
I don't understand what you said about the majority, and that sounds like an interesting question. Was that like, you have results on the last word on your slide?
On the?
What did you say about the last word on your slide?
The P majority? We don't have results on this model. We have some simulations that suggest that there's also going to be a similar phase transition. Only now, if we require a majority of greater than 3/4, it will behave similar to consensus. You'll get something polarized. And if you require majority between half and 3/4, it will be something similar to a triangle distribution. A bit on a continuous distribution that looks kind of the same. But analyzing these kind of rules is much more difficult because you basically need to track 2 points. So in the model we studied, you only need to track just 1 point, so just the P quantile of some fraction. And for P majority, you'll need to track both the P quantile and then 1 minus P quantile, which makes it much more difficult to analyze. I guess, not sure it was clear, but that's kind of the reason why this is much more difficult, but also it's very interesting. Yeah. Any more questions?
So could you think about design, like if you had some kind of objective for the group, what would be the best rule? It seems like
Yeah. I guess it's a question of what your goal. Basically, consensus is probably not a good idea. That's, I guess, the main conclusion. Yeah, not sure what else concrete I can say.